Okay.
Yes, we are there.
It's okay now.
Give me a second. Yes. Right. Right. Really engaged. Yes.
Super. So, welcome everybody to the first seminar of this semester. Great pleasure to welcome Alexis Finoguenov for this first seminar of our academic year. Now, Alexis and myself go, a few years back. We know each other for some time. He did his PhD at CFA. Well, his PhD was from the from Russia, University of Moscow, if I remember well. But most of his PhD was actually done at CFA, Center of Astrophysics, where he worked on galaxy groups and the X-ray emission. And then after completing his PhD thesis, he moved on to Potsdam for a short period of time, and then from Potsdam to MPE, where he was a postdoc or staff scientist for a long time, for deciding to move further north and Finland, University of Helsinki, where he's a full professor now for some time. And he's still working on galaxy clusters and galaxy groups from the X-ray side. And I think this is what your presentation is going to be on, constraining AGN feedback by studying clusters and groups of galaxies for X-rays. And with that, I give the floor to you.
Okay. Yes, nice to be back here. Last time I was here, we had a team meeting on Canada Sound here. And I don't see anyone from the team in the audience. But yeah, Hayes was around, although it was not working. I should do sound. Right. So, well, I guess this visit was created when Manolis was visiting Helsinki recently as an opponent of a PhD dissertation of Archivit and then on AGN clustering. And the reason I'm here is that we have published so much on AGN clustering that we run out of ideas and we need new ideas. And so I came here to get new ideas by talking to people. But then I was also asked to give a talk, and I wanted to talk about something I was working on in the last years, but which has a connection to AGN feedback. So and I think it's a very nice connection. And it's started to be actually popular. So a few years back, nobody was talking about this, and now I start hearing about this more often. So, but that is what I wanted to kind of talk to you about, to inform you about things that happen in the field of galaxy groups, which is related to AGN feedback. So, so I put Euclid in the title because, in fact, all this is supported by Euclid. Okay, and I will explain you why in details. And I wanted to list my PhD students who published papers on this. It's Anna Damstedt, Hossam Halil, Jacob Kosowski, my collaborator, Gaston Gonçalves, and also mentioned two consortia. One is Spiders. This is the follow-up of galaxy clusters on SDSS4. That was done. Spiders has Rosita in the name here, was finished before it was actually following up my samples. So I got 50,000 spectra from that. So I will show some results on this. And XGAP is it's another collaboration that started currently led by Dominic Eckert, and we started this at MPE, basically next door to Antonis. So and I will show some of the results from that. Okay. So so Euclid will be measuring the power spectrum. I mean, of course, it's not the only experiment that measures power spectrum. I am submitting a power spectrum paper myself, maybe next week. So Manolis worked on that. I think one of the pioneering works. I will be if you will show the references, see my references, I will be quoting a lot of Manolis works in my talk. But the point here is that when you compare your measurements to the theoretical prediction, this is how you derive cosmological parameters. And if your theoretical prediction is incorrect, your cosmological parameters will be biased. So, and what happened is that and the Euclid is one of these first experiments that the precision went to the degree where this starts to matter. Okay, and that's why I put Euclid in the title. Okay, after that, Euclid we don't need anymore. This is the selling point. Okay, so what you see at this picture is this is the ratio in the power spectrum in between let's say, so in simulations with AGN feedback, okay, and simulations without AGN feedback. And so here we can plot the ratio just to see where the effect is. So on very large scales, small k numbers. So k number is the inverse of the scale. Okay, so this would be 10 megaparsec and more. Everything is fine. Okay. But then if you go to 1 megaparsec, that's H inverse, you start to deviate from this simple, from the dark matter only prediction in the power spectrum. And it is in this region that Euclid has constraining power. So if you don't use this, then the question is, why did you launch Euclid? Okay. Well, so okay, so the other question is, okay, is it really important? Here's the plot showing what happens in the standard sigma 8 omega meta plane, and location of these solutions is due to incorrect analysis of the power spectrum, while the simulated value is here. Okay. So it means that the systematics associated with AGN feedback is huge. Okay. Also, for the energy equation of state, the systematic is huge, so it has to be understood. Second thing is related to where this shear power spectrum is used in Euclid analysis. So this is this plot. It shows the Euclid forecasted constraint on the dark energy equation of state, and these envelopes is the contribution of the shear power spectrum. So basically, it is redshift point two, where it is most constraining. So Euclid has.
Alexis, can I interrupt for a second?
Yeah, sure.
Do you mind if you actually define omega matter sigma AW, because not everybody's a cosmologist here.
Right. Well, for the, let's say, if you're totally ignorant of this, it's enough to just know you have to account for feedback. Okay, so the only thing that kind of matters to me when I show this plot is basically the expected constraints are very tight, but the systematics is a placement of this constraint is very high, and that is for any parameter, whatever you measure, right? If you see the systematics is much larger than your error, you cannot measure things. Okay, that is well, okay. So then, of course, we can say that we have the omega matter. It measures the density of all the matter in the universe. So this is expressed usually in at redshift 0, so because it tells you volts. And sigma 8 is the amplitude of the fluctuations. So that is just a normalization of the power spectrum, if you like. Okay, so, but the word fit when, and I'm sure most of you did the same. For a while, when you hear the word feedback, you kind of stop listening to the talk because it means that people don't understand anything, right? I mean, that's usually my impression. So, and that's why I never, bothered. I mean, these plots were done by Elisabetta Cimboloni, and I was visiting them in Leiden at that time. And I said, okay, yes, you show these. So what do we do? And then a few years later, they actually made this plot. And only at that point, I said, okay, now we are talking, something serious. Okay, so what this plot showed, they measure this ratio in the power spectrum. They have selected a given scale where they want to measure. So this is this K 0.5 H inverse megaparsecs in. So that is basically, if we go back, right? So they are looking here, okay? They took every simulation that people produced, okay? Well, obviously the most recent ones in order to kind of use the most recent ones. So, and we knew already at that time that all the simulations, they have huge differences in AGN feedback. And that actually is shown here, so that because they have very different implementation of AGN feedback, they actually produce huge difference in the meta-power spectrum. But then they went to measure in the same simulations the baryonic fraction in groups and low mass clusters, okay, at plus 10 to the 14 solar masses. And they could put all these simulations on the same kind of curve, and which for the first time start making sense. So the thing is that, of course, there are all these different prescriptions on the feedback, but the link between those prescriptions and the effect of the feedback on the outskirts of Gauss group is uniquely linked to the effect of the feedback on the meta-power spectrum. The reason for this link is if when one analyze this in more detail, is that actually the main contributors to to the matter power spectrum on those scales are groups and classes of galaxies, and galaxies themselves contribute on smaller special scales or higher k values. So this only works at this k. At different k, it will not necessarily be linked to the galaxy groups. So, but the conclusion is that by studying the outskirts of galaxy groups, we can at least solve the feedback at this feedback effect at these scales. This kind of green rectangle shows that the constraints that were available at the time on the baryonic fraction. So basically, what we do, we measure this parameter, okay, and then we pick up a simulation out of this or simulations that is the correct one, okay. So this simulation will can be used to analyze Euclid data. That's the idea. So,
but only on specific scales.
Only on this scale, right? So I would say that if the more you learn about how feedback operates, so like if you study lower mass scale, you can okay. So let me just go here. So we've basically, once we study groups and classes of galaxies, we can start using this part of the power spectrum. But in order to use this part, we need to understand how AGN feedback operates on the normal galaxies. Okay, so that is then, and that is something to be done. One can also kind of convert the problem, saying, okay, so we're going to use that part for cosmology, and we're just going to measure the ratio and see what is the effect of feedback on galaxies. That is possible too. Okay, but in principle, measuring baryonic fractions in galaxy groups is not that difficult. So, and so this talk is about this. Okay, right. So this is a forward for why we care about finding groups across galaxies, particularly going to the groups regime. Okay, and usually when we talk about cosmology with groups and classes of galaxies, like in the last, well, at least in the 30 years I'm doing this, a standard approach would be to say, in X-ray, we detect all galaxy clusters. The classes that we don't detect in X-rays do not exist. Well, typical cosmology is, as they say, often in error, but never in doubt, right? That's typical cosmologist. So, but we, and galaxy groups, when you try to get proposal on galaxy groups, you'd always receive rejection saying galaxy groups are not important. So now with this new concept, we say, okay, Euclid gonna do cosmology. Forget your clusters. Galaxy groups are important because it helps Euclid derive cosmology. So we keep in the cluster people in the back with this. Okay. So I waited 30 years, now it's my time. As they say, if you're patient and sit, one day next to the river, right? One day the body of your enemy will fall down. The great strategy work. Okay. So, and so good. Finally, yeah. Well, despite this, my proposal for getting money was rejected because the reviewer said dark matter don't exist. Forget it. Okay, well. And he proudly put his name, Pavel Krupel. Okay, so meet this guy next time. I have a few things to tell him. Anyway.
Don't beat him.
Anyway, yes, but nevertheless. So, all right. Well, I hope I don't have to prove that dark matter exists, because that would be would take a lot of time. But in fact, we do have measurements of masses for galaxy groups, and it's all dominated by not by Baryonic. Okay, so all right. So I'm putting a new sample of galaxy groups, and I wanted to do it in a way that we can actually use simulations to model how we detect galaxy groups. Okay, so I mean the very point that again we have a plot like this indicates that the simulations start to deliver a consistent picture of the group outskirts. Okay, and in principle, even now, understanding the centers of the group in simulations is very difficult. Okay, so but outskirts seems to be working fine, and so the idea that I was pursuing is to try to detect groups by outskirts. So okay, so here is the picture where we have galaxies as dots, and they form logical structure, and we have X-ray emission as color, so it's gonna appears here. This some more. This also this. And we can identify them and form catalogs of systems detected by outskirts. And so these are the papers that I'm summarizing in this talk. So we can identify them as EEST. Also, there are different ways of identifying, which I will discuss. And we also can identify all sky with two mass redshift. So this is this is a map of the sources detected on large spatial scales. So we don't know what is outskirt of the group when you go to detect it, because you don't know the redshift of the group. So we have to apply fixed angular scales for the detection, and then later try to understand what these scales of detection bring us. Okay, so and we have, of course, the concentration of sources here due to the that's high. So this is a Rossby sky survey, but it has the deep exposures in any north ecliptic pole area, so there's more sources there.
And it's not homogeneous in flux.
Yeah, it's not homogeneous in flux. Right. So this is deeper. Yeah. So because showing things for sky gives you the opportunity to show nice picture, I'm gonna illustrate the catalog with the 2MRS survey, because it's an all sky survey. Well, all sky only misses little bit in a galactic plane. The coordinate system used to display all sky images in the for the nearby universe uses so-called supergalactic coordinates, in which galactic plane is vertical. Okay, so that's it's historically. I did not invent that. So okay. So in TOMRS we have identified 558 galaxy groups with optical groups having at least 3 spectroscopic members, and if you work on optical groups, then the basic thing there is that your sensitivity towards halo detection increases a lot when you go to when you put when you consider groups with few members. However, if you only take groups with 2 members, or even groups with 1 member, then you are sensitive to a very broad range of masses, which creates, for the identification purposes, which creates a lot of noise. Okay, and the main thing that you have to observe when you do identification is the purity. Okay, so so for that reason, we go down to 3 members.
Alexis,
Yes.
how can you select groups with 1 member?
Yeah, well, every galaxy is a group of 1 member, and we do use galaxies as tracers of halos because we have stellar mass for galaxies. And in fact, I have a catalog in which I use this principle. I use massive galaxies and identify them. The slight disadvantage of doing that though is that galaxy mass is a baryonic tracer, while number of galaxies is less. It's not so baryonic. So we prefer, in principle, but if you want to model things, and that is the whole point, to model things from scratch and simulations, you don't want to use galaxy mass. It's too hard to reproduce. Okay? While number of galaxies is modeled. So the MOCs for galaxy groups, they are around pretty good MOCs. At least 15 years we already have pretty good MOCs for galaxy groups. So that is not even an issue in my mind. So it's the X-ray part that needs to be added. Okay, so here's the plot illustrating what we find. I think the most interesting plot is here. We have all the groups that we consider as a function of their velocity dispersion. In order to measure velocity dispersion, we are only here considering groups with at least 5 members, because otherwise we cannot measure velocity dispersion. Velocity dispersion is a measurement of the mass of the system. And so these are all the groups, and in orange you see the ones that we identify. And so basically we are almost complete at the massive end, and we're doing pretty good at low mass end. So then this is our kind of completeness in luminosity, 10 to the 43, more or less. That's the redshift distribution, and that's the distribution of systems over the NH. NH is the foreground absorption. So explain it a little bit more here. The foreground absorption changes our X-ray sensitivity, and so basically there's some differences in, let's say, log n log s. This is the number of sources function of their flux that kicks in here. That is due to lower sensitivity towards the galactic plane where there is absorption. Okay, and in extragalactic regions, the kind of flux limit of the survey is approaching 10 to minus 12. So, so these are bright sources. The source that we find, and the main thing that we were surprised at that most of them are not known. So you find sources that and people like they publish going to deeper ways, okay, and yet lots of these sources were missing in the previous catalogs. Even in a currently published Rosita catalogs, they only have 73 out of this. I think we have 300 in common, 73 are published, so they miss 200 sources.
But does that the requirement for X-ray detection is it X-ray extended source detection, or you just go down to the noise level and you match with optical?
No, it's X-ray source, and it's a background limited detection because it's large scales, and right, and yeah, so each source is like detected at 4 sigma on this scale and above, and that's the threshold for detection. So okay, but then this plot shows what did we detect. Okay, so for very nearby groups. Okay, so what I'm plotting, it's RE is the extent of the X-ray emission. Okay, so we detect the source, we measure the radial extent, and then we have an estimate of the R500. R500 is the kind of size of the group. Okay, that's supposed to emit X-ray. Okay, so typically when we measure things in X-ray, we always go to R500. If you go beyond R500, you did a very good job on collecting lots of data. It's because it's very hard. So R500 is a typical extent of X-ray emission that was known before we started doing this stuff. Okay, and this R500 is the place where in the simulations they want us to measure the baryonic fraction. So basically, it tells you did we reach R500 or not, and this is extremely luminous. So what happened is that for very nearby groups, we still see the central part of the group. So this ratio is small. But then our best sample is between 0.01 and 0.03, where we sample really well the area around R500 in our detections, and often go to radii above R500. So, so this part basically is what simulations can reproduce. So this whole idea is that I take simulations and I can model what I'm doing using simulations. Okay, so that is the holy grail. Okay, so few more optical scatter plots. So this is how luminosity changes with redshift of the system. So okay, so as I said, our best regime is here. Okay, so this is a kind of complete part. So well, this is a standard kind of a standard change in the luminosity with distance. So I guess here what we see is that the 2-mass spectroscopic survey stops at relatively low redshift. The same sources can be matched to other surveys. This is shown in blue. So the sources themselves would go to high redshift, but 2-mass stops redshift 0.05. So in order to work with deeper optical data, we also use SDSS. So there, what you see here are the in gray optical groups and in black X-ray groups, and these curves just tell you these ones are completeness limit for the optical survey, and the blue ones are the completeness limit for the X-ray survey.
So how, in the second law, how do you actually estimate the redshifts? These are measured redshifts of the X-ray groups from some kind of cross correlation with optical.
Yeah, right. So I'm going to talk about
the red ones are.
I'm going to talk about how we cross correlate a bit. So I have some slides on this. I will get to this point. Right. So in order to measure in order to assign an redshift X-ray source, we have to cross correlate with optical catalogs. That's what Manoli said. And this process, in fact, is also questionable. So part of this effort, we actually developed a new way to how to identify things that we can also model with simulation. And that I will describe in a minute. All right, so just to show a bit of a difference when you do identifications, I plot here what you can obtain if you use 2 mass, if you use the DSS, or if you use the legacy survey, which is photometric survey, that on which we can run a red sequence, cluster finder, and identify system this way. Okay, so basically, so now we look at the lowest redshift, and then of course 2 mass is the dominant source of identification. It all works well. SDSS of course goes deeper, but only part of the sky. But if you move to a higher redshift, then we start identifying more sources using photometric identification methods, just because our spectroscopic data on 2 mass goes shallow. But of course, SDSS is still working fine. And even higher redshift is no 2 mass, just SDSS and legacy. Okay. I'm stuck. Oh. So, and the thing that we realized that actually these catalogs, especially in the south, they provide us with tracers of logical structure. And for example, this huge lack of systems called KBC void in the south is clearly seen even in the photometric data. So this blue is spectroscopic data and pink is photometric data. But even also with photometric data, we still see the void, which kind of on this I even started a project how to detect voids using these catalogs, but it does require a lot of modeling of the selection function, because otherwise you will start finding voids just because of the selection function. So and these plots also show how we trace logical structure in the nearby universe with the 2 mass spectroscopic data. And what was interesting for us that when we plotted all the known voids, okay, that work by Brent Tully and also by Manolis and Spiros, we see that in fact one can trace all these voids, also with our groups. Our groups are kind of making all this bubble around this voice, so that which seems to be pretty nice. So what we can say that, okay, so indeed this catalog seems to be tracing logical structure, local logical structure very well, and in fact Brent already asked me to send him the catalog, so he is already using it for the purpose. Okay, so these are new systems, and we want to understand what are they. Many of them actually were observed as AGNs with XMM because they have active radio AGN. So we have analyzed this data. That's one thing. And then the other thing what we did is we took a representative sample from the SDSS groups, and we got XMM time on it, and that's what XCAP is about. So we're doing both. So yeah, so that's typical XMM image. That's where we measure temperatures. And that's how we do the surface brightness analysis. So we put a lot of annually collect counts, and then we have two mass measurements. One is from XMM in the center, and the other one is from the dynamics. So we can actually measure Hell concentration to see what kind of Hell concentrations we have. So that's a bit more going a bit more into the detailed X-ray analysis. Okay. Well, this is a first scaling relation is between the velocity dispersion and luminosity, and then we compare to the published ones. So there are a few that agrees with us. There's some that disagree, but also we noticed that there were not that many Bayesian methods applied to data analysis. So I think these ones were the Bayesian methods that they tend to agree. The other was the, let's say, sigma velocity dispersion temperature relation. So these are kind of technical plots for people, for people like Elias who study this in different surveys, and particularly this one. This one we found interesting, and at least we can explain things to a broad audience easily with this plot. So it's the standard temperature X-ray luminosity scaling relation. And what we show here are all published scaling relations, okay? And what one can easily see that if you have your favorite scaling relation, we have a point on your scaling relation on both ends. So basically, it tells you that selection effects can change the scaling relation a lot. So if you select this, okay, I thought I quit everything, but apparently not. So selection effects can bias the scaling relations because there is this almost bimodality in the points that, okay, so this is out of battery that you see here.
There is another point that the gray can.
The gray, even this.
Yeah. Yes. The
okay.
button.
Okay. Yes. Okay. So right. So that so this plot shows that understanding the selection effects for Gauss groups is important when you measure scaling relation. And in fact, if you start modeling it with the standard approach, for example, you detect something and then you assume that the rest of the points follow a Gaussian distribution. Well, the ones you don't see, okay? So this may or may not work. Okay. Right. Okay. So I'm going to. So when we studied the and with all these plots that I showed, one can, although the plots are technical, what we can conclude from these plots can be explained to a broad audience. So what we tested there is whether what we see, this appearance of the group is it the result of feedback itself, or it is a result of different dark matter concentration. So on the dark matter concentration, our measurements are like this. They have large error bars, so it's has to be improved. And I think the only thing that we measured here with confidence is that in order to explain these points, we have to assume that there is a large scatter, intrinsic scatter in the concentration among galaxy groups. Okay, so that is one robust conclusion, that scattering concentration for galaxy groups is large. It's not surprising, but it's the first measurement that tells this. And the other thing that we could show is that when we use the scatter in our mass measurements is smaller compared to the scatter of if you just use the temperature, which is indicative that there is a compensation between the various processes, okay? Because the mass, so basically there is feedback. You can change the gas distribution, but the way you trace the total mass doesn't change, okay? So you still have to recover the total mass correctly, and that. So when we say there is no scatter in the let's say here in this relation doesn't have much scatter compared to relation with, let's say, with temperature, it means that the scatter is so there are compensating processes. So the scatter is there, and the scatter is due to AGN feedback being different in the different systems. But in measuring the mass, the scatter is canceling out by the distribution of the gas. Okay, so I hope that's right. So the other parameter that, apart from the temperature, is the slope of the gas distribution, and we call it beta. Okay, so typically systems that do not suffer from feedback, they have beta values above 0.5. Most classes have beta 2/3, so it's 0.6. This is distribution for our sample. Okay, so first we analyze this XMM data, and so this is this distribution. But because all the systems are so bright, we can analyze them in Rosita data, which we also did, and everything is there, well, just in the south. So half of the sample is visible. And so basically, what the public archive lacks is quite a few super flat groups. So the most strongly affected groups are not in archive, but those we can analyze with eROSITA. And that's the eROSITA profile of one group. So tons of signal. Tons of signal. Yeah, these are bright. So the funny thing is this is a super bright sample, very easy to work with once you know there is a group there, you can analyze existing data. But it's not in most catalogs. That is the surprising part. Okay, so this Right. So now we're going back to identification thing. So this plot shows how we do identification in standard way. So so the size of the contour is it's the size of the moon, if you like. There are there's typically 1 million galaxies. If you go reach magnitude 27, right? So there are thousands of galaxy groups. So which one is your counterpart? How do you select the counterpart, right? So one method is to say, I'm going to select the most massive one, okay? So the most massive one, but then the most massive one can be also very distant, and so the typical selection curve looks like this. So you take and this is the the full expression. So you take low mass, low z, or very high mass, high z. Okay, so that is one way to select. For 2 mass, we didn't have to do selection because it's confined to low redshift, so it is all the same. But in principle, okay, so this is different. In principle, this kind of selection bears the problems that actually you don't know what to select. Okay, so that's one thing. Second, when you start saying I mesh X-ray center to optical center, you're already working with X-ray centers, and X-ray centers are not well reproduced by simulations, and so all this work goes to nothing because in your identification procedure, you already violated this, reproductivity argument. And so we have decided to find a method that allows us to identify outskirts of galaxy groups by outskirts of optical galaxy groups. So X-ray, so basically X-ray patterns by outskirts of galaxy groups. And for that, I was on one of the talks, and the radio, and somebody showed that, like, if you want to find characterize how well one picture resembles the other one, you have to measure Hausdorff distance. And so we tried to play with that, and it works amazingly well. But let me describe quickly what is Hausdorff distance and what did we do to it so it works for us. Okay. So the Hausdorff distance is so basically we take two distributions and it finds the maximum distance let's say in points from one distribution to another, and also from and then changes that. So for example, here all the galaxies inside X-ray contour, they are covered by X-ray emission, so their distance is 0. So the largest distance of galaxies to X-ray is found here, either this one or that. That will be the point with the largest distance. Okay. And then the second argument is the largest distance of all points on the contour to galaxies. So it would be, so for example, this point has distance to this galaxy. Okay, so that point has this distance. So this would be the distance. Okay, and so Hausdorff distance is the maximum of these two. Okay. So because we work with real objects, maximum, there could be cases that, for example, I have like this extension, and maybe it's because there is an unresolved point source. So we work with ugly data. Oh, it's not perfect. So instead of maximum, we actually use median. And median value means that bulk of my points should match, right? I do not pretend I understand every single galaxy in galaxy. Also for optical galaxy groups, they suffer from contamination, and the contamination is largest at largest distances. So one cannot be 100% sure that every single galaxy belongs to a galaxy group. And so, but majority should. And so this median argument is a good one. Okay. And what I'll be showing here is that this is our match. MHD is 0.1 megaparsec. And this we discard. The MHD is 0.9 megaparsec. So and you can see by eye that indeed this seems to be a match, and then that seems to be not a match. The funny thing is that some of this group, like this group, you would think that where is optical center? You would think the optical center is here. And then you look at the published optical center, and it's here. Because this is the brightest galaxy. So this is never in any catalog. And then people do stacking, and they stake the center and say there is no X-ray emission. I say, of course there is no. It's there. It's next to it. This.
So you use each galaxy with a weight of 1 in the determination of the house of selection, not weighted by its mass or by its luminosity or by its flux or what.
We don't know.
If you have used a weight, maybe it would be a different.
If you use weight, then you might be weighted. Yeah, it might be a problem. So then we also randomized our X-ray contours, so put them in random places, and so to create random matches to understand where we have to stop in order to keep the sample clean. So this is done. This is the result of our procedure. So the beauty of this is that this is a non-baryonic matching technique, okay? And it's totally reproducible by simulations. But what we see is that we actually recover. This is our line above which we identify 50% of galaxy groups. So below is less. So basically, this is Roswell sky survey. We are already doing it with Verosity. It goes even deeper. We are very complete at the levels of velocity dispersion that one have never reached in X-ray. Okay? So 200 kilometers per second. It's hard. Nobody reached that with confidence. So for the first time, we are reaching these values with confidence, and that is amazing. And these groups, their appearance is very funny. Okay, so that probably is the reason we couldn't identify them before.
Which means funny?
I mean, they're distorted. They are affected by AGN feedback. They're like gas everywhere, and so finding the center is good luck. So that, yeah, but outskirts seems to behave better. These are purity completeness plots of this exercise. Yeah, so we tried megaparsec based or degrees based. And if we use degrees, then we have a problem with the purity, I think, at the high Z. High Z has problem because it's too large distance for high Z sources to allow this. So megaparsec is better. And because we have redshift from optical galaxy group, calculating megaparsec is not difficult. Okay, well, it's getting good. So in yellow would be the groups we would find with standard methods. identification. Most of them we find, so we basically more than double the sample when we do this. And formally speaking, they are the same groups. They just have a problem with the center. Okay. So right. So this slide summarizes what I have told. I don't know what time is it?
Yeah, we should be wrapping up.
Yeah. So basically, we have developed the method, and we have produced the catalogs with this method that is totally modelable. That is something we will be doing as next to actually run cosmological models, analyzing cosmological simulations to see our selection function there. And actually, the samples that we obtained, they already allowed us to learn a lot about the scaling relation of galaxy group regime. And here I'm showing the main result from the catalog paper in SDSS, where we find that as a function of, so we did a lot of scaling relations, and all kind of boring and standard. But one thing that was different is that when we split the sample based on the large scale density, okay, we start seeing differences in scaling relation. So if the environment is dense, for a given velocity dispersion, the group will have higher optical luminosity. It will have higher X-ray luminosity if you select as a compact source. If you select large extended source, the trend is washed out. There's almost no trend. Okay, that is like a main result from this paper. But it means that if you use mass proxy in clustering analysis, you will have a problem interpreting your clustering signal, because your mass proxy changes with the large scale bias. Okay, so in a basically, okay, so I have to explain a bit more. So when we do AGNs, all AGNs are the same for us unless we mark them. Okay. So in correlation function, we can do standard correlation function, or we can do marked correlation function. So for us, the mass proxy is a mark. Okay. So we can always say, oh, this is a cluster. It has a large bias. Let's scale it down. And then you can say, okay, is my scaling down works? Okay. And we did that for all the deep surveys, and it works. Okay. At the same time, we know that the clustering of optically selected clusters is too high for the mass, too high. And now we have resolved this. So basically, you have a covariance between your mass proxy that you use and clustering, and that is a nasty one. Okay. So in order to do power spectrum with optical mass proxies, you have to have not only mass measurement, but also either measurement of the concentration or the measurement of large scale environment. So our message is that if we want to use classes for precision cosmology, we have to describe them not with one parameter, but with two parameters. Okay, so not only mass, but mass and concentration. Okay. So just a quick, yeah. So this slide illustrates which are the systems we did follow up with XMM. So this is in red. So this is low luminosity. These are their density profiles. density is very low. This is expectation from clusters. This is galaxy groups. So the density is always very low. The pressure compared to pressure in clusters is also low, but they here at large radii, they recover. Then this is entropy. That's physical parameter of the gas, indicates how much feedback the gas received. This is a prediction from gravitational heating. That's what we measure way up. So they are all strongly affected by the feedback. And we have one system that is the champion of the feedback. And apparently, we think that feedback happened at very high redshift. And after that, the system is not capable of cooling. And so it tells us that the feedback was there from early on. Which means that, this exercise of constraining feedback has to be done as a function of redshift. At the moment, we only work at low redshift. So, right. So this is a summary of my talk. I have shown you the new samples of galaxy groups that we have created, and most of them are already publicly available. So a few papers we are still in the process of completing. And what we did is we established a completely new procedure of how to detect galaxy groups by outskirts and work out all the problems that are associated with that. Okay, so I mean, in principle, I have more material from, there's more material on modeling with simulations that we already progress there, but I mean, it's all basically confirming that this is a good way forward. So, and indeed, what we found is the evidence that the feedback, the AGN feedback is very strong. So, so basically what happened is that if it's previously published samples, they're mainly systems with less affected by AGN feedback. And now we're adding so many groups that are strongly affected by AGN feedback. So this overall weighting on AGN feedback basically moves to stronger feedback. So in these kind of plots where you pick different simulations, you would pick one with the stronger feedback. So so basically, with these samples, we think that we can supply correct interpretation, the correct simulation for interpretation of Euclid results. That is the point of the project. Okay, I'll stop here.
Alexis, I have quite a few questions, but I will not monopolize the discussion. We can discuss it later on. But I would like to ask you an initial, very fundamental question, which has to do with what I mentioned in the beginning, that your original underlying sample of X-ray extended sources from RAS is not flux limited, homogeneous. It's not homogeneous in flux limit on the sky. Is that a fair statement?
Okay.
Because if it's not, then you can do individual, of course, groups and way of development studies, but you would not be able to do any really large scale structure studies, because in some parts of the sky there are deeper.
No, you do the modeling. I mean, so I produce so basically like for power spectrum, I will produce the density of sources, expected density of sources as a in 3D, and that we use for normalization. For cross correlation, we produce random catalogs that has this in it. So no,
But you can have random catalogs that have the same sort of flux dependence.
Yeah.
But nevertheless, if you want to if you want to do a study of the 3D large scale structure, you have parts of the sky which would have more low luminosity objects, groups, and others that you will not see them, not because they're not there, but because you don't have the flux.
Well, that's so for the void finder, we basically the thing they want from me is this model. It's a kind of number, my sensitivity, that's functional position phrased in a number of objects I'm supposed to detect. That's the but actually here we stopped doing the other trick we did was because of different depths. You get difference in the source extent just because of that. So we decided to do it's called the corners of equal baryonic over density. So when you do the corners, you can actually enforce equal over density. And that allows to unify things. It will also so depth is gone once you do that. So yeah. Yeah,
you have
also tricks.
You have to take it back.
Yeah, but it's actually good one. Yeah. So.
Any more questions, including online? Yeah. Yes.
Alexis, thank you for the talk. Having these AGNs in groups, okay, and then detect them in X-rays. Some of the AGNs would have emission, so you have this contamination for the X-ray emission from AGNs in the groups, which may be a problem, right? In deriving anything. I mean, also the detection. Probably some of them are boosted by the AGN, some of them you will lose them, but also using them for cosmology is not a problem. How do you treat with AGN contamination, especially in groups which don't have much?
Right. So so when we do this detection, we detect point sources and we remove them from the analysis, so they are not in the picture. Okay. So these are the scales of, you can see a fraction of degree. So these very large scales. So
I think what Elias is saying is, how do you remove of the extended emission, the contribution of point sources?
well, basically so there are always there are point sources everywhere. I just detect them, and it's a multi-scale image decomposition. Small scales are AGNs, and I remove them. Large scales are groups, and that's what I analyze. So the main contaminant are actually supernova remnants. I have basically confirmed all supernova remnants. And previously, there was this missing X-ray supernova remnants problem. It's gone. Because it's the same problem. People don't know how to detect the sources. It's amazing how many. I have excess of sources over galactic plane, huge excess. And you look at this beauty, all radio supernova remnants are detected. It's all there. So it's the only, we also, when we identify supernova remnants, there you can also use X-ray image and radio image, and the identification is matching two images. Because otherwise, how do you know it's supernova? It's trickier than gas groups are easier. Supernovas are trickier for identification. If like radius is not there or radius is too complex, then it would be hard. But yeah, I had one summer student who basically eyeballed all supernova remnants with the sources. Really nice, especially towards the central. Well, what's called? So towards the Sagittarius star, there's like this amazing stuff. But it's these are the main attempt. You know, galaxy groups probably half of the sources, and the rest 3,000 is all galactic sources. Yeah, it's very interesting. But no, so answering to your question, so for us the reason we went to this very large scales is to avoid AGN. So also for example, with Rosita, we also use almost the same scales, somewhat lower. And I still have 1 million AGNs that I detect and I remove. Okay, number of these sources in Rosita is like 15,000, something like this. So, but it's if you want to explain the source as 10 AGN, fine. But usually it would, I would say this matching would not necessarily work if you try explaining this for AGNs. That's the scale set. It's usually AGNs affect the detection when, let's say, you have a PSF and you work twice the PSF. And here is like 10 times PSF, it doesn't matter. If you just step away from PSF, the more the better. Of course, when you work on small sizes, you do cosmology, you go high redshift, you find high redshift clusters. This is what, for that, you read Google paper, take this catalog. Don't ask me, okay? I work low redshift galaxy groups. I do things upside down. So, for a reason.
Okay, I think we should close it here. We are well over an hour, but Alexis will be here for the next week or so, I guess, right? So if anybody wants to find him and chat with him, he will be at the president's office, I think. So yeah, we close the seminar here. Thanks again.